urgent but analytical. When a bearing fails inside an Atlas Copco GA series compressor, it means immediate production halts and massive financial losses. An unexpected air end failure can bring an entire facility grinding to a halt. For decades, maintenance teams have tried to predict these failures using standard vibration sensors, or accelerometers. These sensors are designed to measure the macro movement, the physical shaking and rattling of the equipment housing as the machine runs. There is a fatal flaw in relying on macro movement. By the time an accelerometer actually detects a low-frequency shake from a failing bearing, the compressor is already dying. The damage is severe, irreversible, and catastrophic failure is imminent. This diagram shows the difference between that physical shaking and a technique called the shock pulse method. Instead of feeling for low-frequency rumbles, SPM acts like a highly sensitive microphone tuned to a specific resonance frequency of around 32 kHz. It listens for high-frequency stress waves traveling through the metal, detecting the microscopic crunch of tiny debris being crushed between the rolling elements and the raceway. These tiny collisions generate faint stress waves long before a standard vibration sensor picks up an anomaly. Surviving industrial equipment failure requires abandoning the wait for macro movement. You have to start tracking the micro signals, and you have to track them over time. Getting accurate data starts with a pristine setup. You take a perfectly healthy, newly installed compressor, run it at full load and maximum speed, and establish a clean zero point. This graph shows how we map the health of that machine over time. The bottom flat line is the dBi, or initial value, which normalizes the readings based on shaft speed and bearing diameter. Tracking just above it are our two operational metrics, the dBc, or carpet value, and the dBm, or maximum value. The carpet value, dBc, is our direct indicator for lubrication health. A low, stable line proves there is a thick, healthy oil film separating the metal surfaces and preventing any friction. Let's move the timeline forward several months to our first real-world scenario. Notice how the dBc line begins to trend upward at a steep angle, while the maximum value, the dBm, remains completely flat. This specific divergence in the data tells us the oil film is thinning out. The bearing is running dry. However, the flat dBm line confirms the metal itself has not yet sustained any physical damage. This is an early warning window requiring immediate intervention. The maintenance team must investigate the lubrication system, check the oil viscosity, and take fluid samples. Acting at this precise data inflection point, before the dBm damage line has a chance to rise, stops the trend line dead in its tracks and prevents mechanical bearing damage entirely. This chart shows what happens if that warning is ignored. The carpet value levels off in a highly compromised state, and the previously flat damage line, the dBm, starts a steady, irreversible upward climb. That rising maximum value proves the bearing metal is taking active physical hits. The components are now suffering from structural fatigue, pitting, and microspalling across the raceway. At this stage, the metal will not heal, no matter how much clean oil you pump into the system. The team must begin planning for an expensive air end overhaul before the unit tears itself apart. If the machine continues to run, we reach the final scenario. The bearing is actively failing, tearing away chunks of metal debris that further contaminate the remaining oil. The data reflects this total systemic breakdown, as both lines shoot upward in tandem. We map this escalation using specific severity thresholds. A 15 decibel increase above the baseline signals an attention state requiring intense monitoring. A 25 decibel increase triggers an alert state, meaning visible heavy wear is present on the rollers. A 30 to 35 decibel spike is the solid red alarm threshold. Crossing this line guarantees catastrophic failure. The risk of the air end seizing and destroying the drive motor is extreme, requiring an immediate machine shutdown. There is one notable exception to this curve. If the data shows sudden, erratic, isolated spikes instead of a smooth climb, it usually points to a loose piece of contamination or microscopic pitting caused by electrical discharge from an ungrounded variable frequency drive. A single high reading on a shock pulse meter is just random noise. But tracking the difference between the lubrication line and the damage line across a long timeline gives you the exact anatomy of a machine's deterioration. The true power of the shock pulse method relies heavily on the rigorous, consistent logging of data over thousands of operating hours. To build a reliable trend line, the measurement environment must be identical every single time. Readings must always be taken when the compressor is at full load, and for variable speed drives at the maximum repeatable speed. Taking a measurement on a cold or unloaded machine introduces chaotic variables. The rolling velocity changes, the pressures drop, and the resulting data corrupts your trend lines, making them entirely useless for predictive diagnosis. Plant managers ultimately choose between two operational realities. You can either spend your time reacting blindly to unexpected downtime and collateral damage, or you can use the divergence in your data to order replacement parts months before a component actually breaks. Establishing a firm baseline and tracking its evolution allows you to schedule maintenance precisely when the machine demands it, turning an expensive, chaotic fire drill into a strategic shield for your multi-million-dollar assets.